Lab 4, Circuits. The purpose of this lab is to use the loop rule and the node rule to predict the behavior of circuits through an online model. As for the results, the experimental and the expected values of voltage and current matched up. The light fizzled out over time as the capacitor got charged, and it took 4.74 seconds to charge the 10 ohm bulb, 7.94 seconds to discharge the 10 ohm bulb, 6.44 seconds to charge, and 10 seconds to discharge the 20 ohm bulb. And for both, the current slowed down over time while it was charging, and the current would start back up again and then fizzle out again as it was discharging. As for the RC current section, or RC circuit section, the observed RC matched with the expected RC, which was 6 seconds. As for the fundamental physics principles, we really just use the node rule, loop rule, Ohm's law, and pretty much the principles with steady-state circuits. Here's the model used. It's an online ideal model of a circuit. We assume that the resistance of the wires and the resistance of the ammeters are negligible. The EMF of the battery, of course, will be the sum of the potential differences across the capacitor and the two resistors. Here's the first part of the experiment, where we assume that the circuit is the system and the surroundings would be everything else. The expected current was 0.02 amps. The calculation is right there, and the observed was the same, 0.02 amps, but it was negative whenever we flipped the batteries. The voltmeter readings, of course, were 3 volts with 0 amps for the current, and the reason why there was no current was that it was an open circuit. And if it's an open circuit, there's no current, and the voltage will remain constant and equal to the power source, which was 3 volts, because there were 2 batteries, 1.5 volts each. Here's the next part of our experiment. It was where we found the round trip potential, and basically everything read 0 volts except for the resistors, with negative 0.96 volts for the 47 ohm resistor and negative 2.04 volts for the 100 ohm resistor. The batteries, of course, were 3 volts, and whenever you combine these numbers, you get a round trip potential of 0 volts, which lines up with the loop rule, where V loop equals 0. The current, of course, was 0.02 amps. Adding the voltmeter does alter the current, but the change is not significant because the voltmeter has a very high resistance, and thus very little current flows through it, which leaves the path of the current flowing through the circuit unaltered. And then here's a photo of the graph that I drew based on what I found. As you can see, the drop in voltage for the 47 ohm resistor is a lot less steep than the 100 ohm resistor, which makes sense because the lower the resistance, the less effect it would have on the voltage. Now, whenever I added an ammeter in parallel with one of the resistors, the reading increased to 0.06 amps. Now, why does this happen? Well, since there's less current going through the 100 ohm resistor, because think about it, there's the same amount of current as previously, but there are more elements in the circuit, there's less current to go around, and thus less current can run through the resistor, and as such, the reading would go up, because the resistor can't have as much of an effect on the ammeter's reading. And then here are my 4 values here that I calculated using the potential difference of each element divided by the ammeter reading. It was 48 ohms for the 47 ohm resistor, 102 ohms for the 100 ohm resistor, and 0 ohms for both the wire and the ammeter. And this would be for the resistance of these elements. Moving on to the capacitor section, the light fizzled out since the capacitor gets charged over time. Whenever connected, the bulb was bright, and then it fizzled out over time, and when disconnected, the bulb burns bright again, and then fizzles out over time once again. And I already discussed these numbers previously. Moving on to the RC section, you can find that the slope that I got from the data collected was negative 0.1664, and whenever you take the negative reciprocal of this, you find that the RC was 6 seconds. This is my observed value. The expected value, of course, is the 30 ohms of the light bulb multiplied by the capacitor, which would be 0.2, which gets you 6 seconds, so the expected matched the observed. Now, since I used an online model with very ideal conditions in place, it's not likely that the data is inaccurate. With the only sources of error really would probably be the charging and discharging times, since I took the data using a stopwatch on my phone. Answering the first what if question, we can't assume that the resistance of the ammeter and the wire is 0, so the contributed resistance of both elements would likely produce a current lower than expected. The resistance of the wire would cause the capacitor to reach full charge slower than expected.